All right, welcome, MS-DOSX folks. Everybody else who's in here is welcome to stay. Just please try and keep your voice down so that people in MS-DOSX can hear, and also because we're recording too. So today's overview is going to be on Core Audio. It's one of the frameworks that's part of the standard SDK. Small confession: back when I was developing games, a lot of the sound and music and audio libraries were all very custom, or they were tailored to a driver. So most of it was roll your own stuff. So now diving back into Core Audio, I'm super overwhelmed by the amount of functionality in Core Audio. It's akin to video in the amount of services that it provides and things that it can do and functionality that it has. So here's what's going to happen. I'm just going to go over and give you a quick 10,000 foot up tour of Core Audio. Any one of these subjects that you are interested in, there's a ton of documentation. In fact, almost all of this comes directly out of the developer documentation. The developer documentation is very complete, and they have a lot of great illustrations, which you'll see up here too. This is more of a summary, and just kind of get your appetite whet for this. It also will give you kind of an overview of what functionality is available to you in terms of audio. I think you'll be pretty surprised at how much functionality there is and what you can incorporate into your projects. So first off, what is Core Audio? Core Audio is this entire collection, starting down at the hardware level and working its way up to the application level. It's layered as typical frameworks are, where you have device drivers that are talking directly to the metal, and then providing access, higher and higher levels of abstraction and access on the way up. Some of the individual pieces here are audio units, which are plug-in interfaces that Apple makes available, and I'll show you a lot more of this. That Core Audio is very heavily tuned as a plug-in architecture, and also supports digital signal processing at the hardware level. There's also a ton of support for reading and writing a whole bunch of different file formats, not just audio files, but data files, music files, even the AIFF tracks in QuickTime movies, or any actually audio tracks that are associated with QuickTime movies. There's also plug-in file formats for handling your own custom file formats. If you've got your own formats that you want to support or use, a cousin of mine wrote a lame encoder using Core Audio, and then there's OGG support. There's a whole bunch of different types of unique and custom file export and import units that you can use and that you can write. And then there's also support for constructing chains of audio effects, and that also includes chains for audio input conversion, file conversion, effect application, output, whether it's to the speakers or to a file or to a MIDI device. And I'll talk some more about that in a minute. And then there's also scalable multi-channel input and audio input and output. And this audio, just as a preview, encompasses not just regular digital audio that you're used to, sampled digital audio, but also MIDI data, which is exactly what this next part is. So Core Audio has full support for synchronization of audio and MIDI data during playback and recording. MIDI is musical, should have looked this up, musical interface, digital interface. No, something like that. I'll look it up. But it's essentially, I mean, this is a really, really old format for describing events on what started out as just audio hardware, like a keyboard, but now has grown to controlling lights and controlling movable stages. Blue Man Group uses a lot of MIDI data and a lot of MIDI shuffling to handle a lot of their show, all aspects of their show. And Core Audio supports not only a ton of MIDI import, output, and playback, but also synchronization with digital audio tracks and video tracks. There's also a standardized interface layer for the hardware. There's an abstracted, the HAL, the hardware abstraction layer. There's also a layer on top of that that presents to the application, as an API, a standard way to interface with input and output hardware that you can plug in a variety of different ways, and using USB or FireWire or PCI, et cetera, any way that you can plug a piece of hardware in. Core Audio has probably got a hardware abstraction layer for it already. So, for instance, in a typical audio, say this is a small audio recording studio with a mixing deck. We have a microphone and an effects processor as input. You have a guitar and a distortion box as input and a keyboard input. We want to output to monitor speakers and output to a reel-to-reel tape recorder. For instance, the microphone has got a hardware abstraction layer. Then it's on top of that is presented the audio unit hardware abstraction layer, which is the API for you and your use. It's a very general way to access the hardware and abstracts away a lot of the unnecessary details from you. Putting this all together, you can end up with a full recording studio using every single piece here comes from the Core Audio framework. Here we've got the hardware abstraction layers and the audio unit abstraction layers, Core MIDI for the keyboard, going through the instrument unit into a mixer unit. I remember I was talking about audio units that Core Audio is made up of. Audio file converter and services to read and write data to the hard drive or to memory, and then another audio unit hardware interface to send the actual audio to speakers. Here are some of the interfaces that Core Audio provides you. That should be over there. Audio unit services, which is the plugin architecture, an audio processing a full audio processing graph API, and I'll talk about that. I have a slide about that in just a second. There's a ton of audio file reading and writing conversion services. There's the hardware abstraction layer services. There's a whole music player API that's not only MP3s and digital music, but also MIDI music, and it can all be synchronized. Then there's the core, the foundation framework for the core MIDI services, and a MIDI server, so that you can funnel MIDI data through your machine and have it act as a synchronizer and handle a lot of conducting the input and the output. Then there's a Core Audio Clock API, which I'll talk about in a second too. There's the OpenAL, the Open Audio Library, which is the audio version of OpenGL, which is 3D sound processing. I'll talk about that in a second too. And then there's the System Sound API, which is probably the most quaint API out of Core Audio for playing back system sounds. So replacing sysbeep, if anybody remembers that from a long time ago in Pascal. So audio unit services, like I said, lets you create and manipulate audio units. I'll show you a breakdown of that a little bit later on. The audio processing graph API is basically lets you take audio units like a compressor and a pitch unit and then an output unit. It allows you to connect them together And graph, the audio processing graph, it's not, this isn't like a spectrum analyzer or frequency analyzer. This is like a graph, as in directed or undirected graph, where you can connect all of these units together, and you can actually connect units into subunits and put them into another full unit. This is an example of an instrument with a delay and a mixer and file input that goes through a compressor, pitch changer, and a generic output unit that goes to the mixer unit that results in a final output unit that you can also connect to and export out to a file or play back on a keyboard or play out on speakers, or all of the above, all in synchronization. The documentation has examples of how to use this graph architecture. Here's an example of a correct and an incorrect usage. There are specific rules for what can go in and what can go out, but the plugin architecture itself is really well designed in the way that you can connect all of these things together and create some really powerful input and output capabilities. The audiophile and converter services have a number of, and I've got it towards the end of the slide, a number of audio converters, both real-time and offline. There's file format information so that you can take a look at files. Quick View is an example of this, where you can take a look at files without actually having to read in, parse, decompress the entire file. Audio metadata that you can attach to an audio file, that you can tag an audio file with, that shows up in iTunes or shows up in a Spotlight search. And then there's the core audio file format, which is kind of like the base format of an audio file that's used pretty heavily in Cocoa. So the hardware abstraction layer services, like I said before, it presents, gives to you an API, an SDK that abstracts away a lot of the nitty-gritty the hardware, the metal details, and gives you a consistent and clean way to interface with your devices, with your input and output devices. So here's where the hardware abstraction layer lives. It lives above the I/O kit, the kernel's I/O kit, and handles the transition to the application level services, the higher level API. The music player API, basically it sounds pretty generic and pretty general, which it is, but incredibly powerful way to take and play back and arrange a whole collection of music tracks, whether they are in digital audio or in MIDI format. GarageBand is an excellent example of the power of the music player API. The core MIDI services and MIDI server services. Here's a blurb from the developer documentation. I'm not going to read it to you, but essentially allows you to work with MIDI data in a clean and consistent way. In the past, MIDI data, the MIDI file format was well known, but people started adding customization to it so that they control different devices. And so they started to have different formats and specifications. All of that is abstracted away with core MIDI services to give you, to allow you to do very basic note on, note off, pitch, velocity type of instructions in a very strict time sequenced and synchronized sort of way. It's really interesting to look at, even if you're not planning on using any kind of music in your application, your Mac application or iOS application. It's really interesting to take a look at this framework. It's pretty amazing. So here's an example of some of the core MIDI services. So here we've got your application sitting here, and it communicates with core MIDI. The MIDI server is constantly running. You can spool it up and have it constantly running in the background, so it can be listening for and sending events to a guitar that's connected to your machine via MIDI and or a keyboard, and keep them all in sync and record from them in real time and play back in real time. Here is another view of that. Here is using different types of inputs, FireWire, USB, and PCI. Here's your layer, the core MIDI layer, and the MIDI endpoints. You can read more about those in the documentation if you're interested. Here's the MIDI server that's basically responsible for keeping things in sync with each other using the clock. This is all user level access. Here's all the kernel level access where you've got the I/O drivers for USB and PCI, and then the actual devices themselves. So the clock API, the Core Audio Clock API, lets you synchronize applications and devices. It's not just for audio. You can actually use it for a lot of different purposes. NS Timer is typically how you handle less finely grained timing and to be able to fire off, kick off events at specific times. The Core Audio Clock API is kind of specialized, but it's very, very precise, and it's a pretty amazing way to keep things in sync, to keep time things in sync. You can also have it, you can also set it to trigger off of specific events or external hardware inputs, even MIDI. Beat codes and time codes can trigger the clock API, and essentially what you've got is you have your playback rate that you can adjust, and it keeps all of this stuff in sync for you. You don't have to try and do the math and try and keep things in sync time-wise. You can use the hardware time, the time that's coming off of the CPU. You can use just the raw samples that are being played back in an audio file. You can send those out as video time codes, SMTPE time codes, or media times, like beats, like in a musical score. All of these things are converted by the clock API in a way that you only have to worry. You can only worry about one clock format, and it takes care of all the rest of it for you. It's pretty cool. The OpenAL, the Open Audio Library, will let you record, playback, and manipulate sounds to audio sounds and MIDI data to play back in three-dimensional space. Nowadays with 5.1 audio, this is much more common to use, much more commonly used. In the past, and it still supports this, even with stereo speakers, there's psychoacoustic models that you can use to create the impression or create the effect that an audio signal is above you or below you, depending on the pitch. Also, the delay can make sound farther behind you or sound closer to you. There's all kinds of really cool tricks that they can use on headphones or with stereo speakers. The OpenAL library abstracts all that away from you, so you can just say, play a sound in this 3D coordinate system, play a sound here, and whatever hardware is connected to the machine, whether you've got a full 7.1 audio system set up or you're just listening on headphones, it'll do its best to try and position it in 3 dimensions and play it back in a way that you perceive as coming from a specific location in space. That's also really fun to play around with too. There's some cool demos out there for that. And then there's the System Sound API, which I mentioned at the end, and it's just the standard way to play the sounds that you have in your alerts folder. It greatly simplifies a lot of these core audio calls. Can start to get pretty complicated, especially when you're starting to deal with time and things like that. This is a way that you can just play simple system sounds, whether it's on an iOS device or Mac OS X. So here's an example of 6 different, very common tasks that are done in core audio. Reading and writing audio data files, interfacing to various hardware devices, the audio unit hardware abstraction layer, using a combination of devices in concert with each other and in sync, creating audio units that you either creating or using audio units that are provided for you, or creating your own, like a reverb or an echo or a pitch bender. The system provides you with a lot of those. I've got that's in the reference material. I've got a list of those. But this is also a way that you can create your own audio units, and it's not just for playback. It's also for import and export too, if you want to create your own file format. And then handling raw MIDI data. So reading and writing audio data goes through the extended audio file API. It basically abstracts all of this away from you, but you can dig under the hood as deeply as you want to and create your own audio units that convert, and read, convert, playback, and save audio in any format that's currently supported. If it's not supported, there's a full API for creating an audio unit so that you can create your own audio file format or mixture of audio and MIDI data file format. Then there's interfacing with hardware devices. Basically, it takes the hardware and abstracts it away from you so that you can either write your own audio unit hardware abstraction layer if you've got your own piece of hardware that you've created and you want to create an API that you can present to a user or a developer to use your device in a consistent way, or you can use the supplied audio unit hardware abstraction layer to talk to common devices like keyboards or electric guitars. Like I mentioned before, the audio unit hardware abstraction layer can take external devices and then through the input-output kit, the I/O kit, that was the layer that sits above the actual hardware itself. It can take and convert the data into a format that you can use in your own audio units, and then you can convert data that you've created into a format that can be sent out to external devices, whether you're sending it out to a speaker or to like a keyboard. Skip this, just more details about the audio unit hardware abstraction layer. Aggregate devices, you can take and at any level of abstraction, you can take and combine all kinds of audio devices and input and output devices and make them appear and look like one single device, which is pretty cool. If you remember the graph that I had shown you earlier that showed you all of the different units that you could put together, the subunits that you could put together, and the units you could put together. Well, you can do the same thing with hardware, and you can make hardware act as one unit, full input and output unit. Creating audio units and hosting audio units is a bit more complicated. So it's a good idea to just go directly to the documentation. I'm not going to even start to talk about writing your own audio unit. It's a pretty involved process, but the full support is there, and it's also pretty amazing to read, even if you're not interested in actually creating a unit. Taking a look at how Apple handles that transaction between the hardware layers is really interesting. So MIDI data, SMF files are typical MIDI data. They can be read in as a tempo track, which all goes to the Core Audio clock API, and then events, MIDI events that can trigger not only like a keyboard but also lights and stage effects, whatever you want, whatever has a MIDI interface, this can handle. So MIDI sequence playback, which is just basically parse a MIDI file and look for event data and clock data, and then run it through any of your audio processing graphs if you want to add instruments and you want to add effects on those instruments, and then play it through an audio device, or actually save out the MIDI playback to a file that you could say burn to a CD. There's also device playthrough, where you can send MIDI events through the machine. It can trigger actions on the machine to control other hardware, and then that data can still go out to the device that you are presenting data to. So you can have a keyboard run MIDI through it, and run MIDI through your machine, and you play on the keyboard. It handles all the MIDI data just as it normally would, but your machine can also be in sync, performing various actions according to MIDI events. It's pretty amazing, actually. File recording. So you can, just like with GarageBand, you can play things on instruments, on MIDI instruments, and record them as MIDI data, which is typically much smaller than a full digital audio file. It's basically just a sequence of note on, note off, pitch, and velocity. So they're very small files, and you can. What's cool is that you can transpose instruments just using the audio processing graph API. You can play something on a keyboard and then play it back on as a trumpet later, really easily. Then there's mixing various audio sources. So you can, while something is playing from memory, you can stream from the hard drive. You can run it through, say, a generator. If you've got your own sound generator, you can run it through the 3D mixer unit, so that now you can place your sounds in 3 dimensions. This is used in games, a lot of games nowadays, and then run it through your output device. Meanwhile, you've got MIDI data that's coming in as well, and it's keeping everything in sync. Taking a big step back and putting it all together this is basically what it looks like. I won't go through each independent portion of it, but there's a lot of attention to detail and a lot of care in keeping all of these synchronized. This is typically a really difficult thing to do. In the past, this was all really difficult to do, and also you had to do a lot of this by hand. Now it's abstracted a lot of this away, and it's very precise. It's really powerful. Here are the frameworks that are part of the core audio frameworks. There's the audio toolbox, which is usually used for digital audio. There's the audio units, which are those plug-in units that you can create, and there's a full SDK for those. There's the core audio kit framework, which is basically kind of the umbrella framework. Core audio as well, core MIDI and MIDI server talked about, and then there's the OpenAL framework for three-dimensional three-dimensional processing. Synthesis, thank you. So here are some of the audio units that come with OS X that you can use. These are just some examples. Here's an example of an effects unit. It's a high-pass filter. And the documentation has got the name of the filter. It has the constant that you use, and it has a description, a full description. In this case, it's a high-pass filter, and you pass it a resonance peak, and it'll filter your audio on the fly in real time. There are system-supplied instrument units. In this case, it's a music device, and it's a virtual instrument that lets you play MIDI data directly out as with a sound bank. Like you could swap in drums, you could swap in different musical instruments, and like I said, this is an example of what the constants look like that you use for the audio units. This is a mixer unit. This is in particular, this is using OpenAL. This is the audio unit, the 3D mixer. Can take different signals and make them appear in space using whatever hardware output you've got. That's all abstracted away from you. Here's a converter unit. In this case, it's the time pitch audio unit, and this lets you change the pitch of a sound or the tempo of a sound. You can change the pitch of a sound without changing the tempo, or change the length of a sound without changing the pitch, which is interesting to listen to, especially if you abuse this unit, this audio unit, which is really fun actually to mess with. Then there are output units, and this is an audio device output unit that basically is the audio unit hardware abstraction layer. This basically is the HAL output layer audio unit that takes whatever digital audio or MIDI data that you've got and can do input and output on various hardware, and they've got a lot of these types already spelled out. A lot of these pieces of hardware that you're already able to access just right out of the box. Here's a generator unit that can generate audio data or MIDI data. In this case, it's a network unit, which is basically being able to stream audio or MIDI data, and it's all handled as an audio unit, and so it's all presented as a consistent interface and a level of abstraction where you don't have to worry about all of the networking details and the TCP/IP timeouts and things like that. It's a really simple way to stream audio, and I highly recommend you take a look at this if you're doing any kind of music or you're trying to do any kind of streaming in your project. Here are the data file formats that are handled in Lion, and actually I'm pretty sure that these are standard. These have been standardized since 10.2. The audio file formats are both input, are for the most part input and output. Actually looking through this list, I don't see any. There used to be some that could be input but not output, or vice versa. All of these, I believe that you can input from any of these formats and output to them. And then there's also data file formats, whether you're talking about the Apple lossless compressor. There's the A-Law. If you're familiar with digital audio at all, you'll recognize some of these, like the Q Design Music. You'll recognize the old Mace compressors and decompressors. There's a full list in the developer documentation. Here are the resources that are associated with the core audio, the main resources. There's an overview that which is a lot of what I summarized here. There's the actual frameworks, the documentation for the frameworks itself, a list of the system supplied audio units that I've shown you, just a brief example of each different type. And then there's a really good site called the iPhone Core Audio Brain Dump, where a guy basically blogs about his experiences using core audio in his iOS applications. Has some really, really good advice and some really, really good tips. Questions?